Okay, let me share. Okay, let's take a look at the warm up. So we're on 10.4, entropy change versus enthalpy change. And entropy is the amount of disorder in a system. And I want you to take a look at the warm up. It says everything around you can be perceived as being in a relative state of organization or disorganization. For each picture below, check the box that applies. Okay, so the first one is a Rubik's Cube. What would you say? Organized. The second one is a messy bedroom. Disorganized. The third is a pile of leaves. Disorganized. Okay. The fourth is Einstein's hair. Disorganized. Okay. We've got a dresser with a bunch of clothes hanging out of it. Disorganized. How about the books on the shelves? Organized. Okay. How about the people walking down the street? Disorganized. And then how about the chessboard? Organized. Okay. So when we talk about entropy, entropy is the amount of thermal energy in a closed system that is not available to do work. And entropy is related to the randomness or the disorganization of something. Okay, so if you've got a really clean room, it has low entropy. If you have a really, really unorganized, dirty room, it has higher entropy. Okay, so when we talk about entropy of maybe a given atom or the entropy of a chemical reaction as it produces product, we're talking about whether like the amount of randomness that we're looking at is increasing or decreasing, whether it's becoming more ordered or not. So everything that we're looking at, all forms of matter, all particles, are going to have some degree of disorder. We're going to be using the letter S as our symbol for entropy. It's a capital S. There are some standard entropy values typically given in the back of a book. I don't believe we have any in the back of our book, but they're typically given so that we can use them to do other things. In this class, we will not be using those values for anything. So the more organized something is, the lower its entropy, the fewer variations that are available or the fewer degrees of freedom. This is related to like if I have a molecule with maybe just one bond, that would have very few degrees of freedom than if I have a molecule with multiple bonds, because we can actually twist around single bonds to create different variations, three-dimensional variations of that molecule. If we are talking about the different variations or the possible configurations of something, we're actually talking about microstates. So what I mean by that is, if I'm looking at a bismuth atom versus a phosphorus atom, you look at where bismuth and phosphorus are in the periodic table. Bismuth is number 83, phosphorus is number 15. Bismuth has got 83 electrons, phosphorus has 15. Since bismuth has more electrons, there are more places in space where those electrons could be. So it has more randomness or higher entropy. Does this make sense? So the bismuth would have more microstates those electrons could occupy. Okay. So when we're talking about chemical systems and entropy, we have to look at one, subatomic particles in atoms like we just did with the electrons in the two different atoms between phosphorus and bismuth, or we could be looking at the organization of atoms in a molecule, like how many different atoms are in a molecule. We can also be looking for the different relationships between things, and I'll get into that. But just so you know, by definition, the third law of thermodynamics defines what zero entropy is. And that's kind of what everything is compared to. So if I have a perfect crystal of something at 0 Kelvin, it will have zero entropy. Okay, that's just a definition that you should probably know. Let's take a look at a few examples of things that I've mentioned so far. The first thing we're going to look at is this table that has all the different noble gases in it. We start with helium and we go to xenon. Helium has got 2 electrons. Neon has got 10. Argon has got 18. Krypton has got 36. And xenon has got 54. Okay, the reason why I listed the electrons is so that we can think about how the subatomic particles in each one of these noble gases is going to sort of have different variations or places in space that it could occupy, which would lead to a greater entropy. Do you see this little tiny degree symbol right here? That little tiny degree symbol that's on the entropy is for standard. Think of this as like a defined quantity. So anytime you see that degree symbol, it stands for standard, and it's usually given in a table. So the standard entropy for helium is 126. Neon is 147, argon is 155, krypton is 164, xenon is 170. So you'll notice that here we have the fewest electrons in helium, and we have the lowest entropy. Over here, we have the most electrons on xenon, and we have the greatest entropy. Okay, so obviously entropy is related to the number of subatomic particles because they can have different places in space that they occupy, different microstates, different configurations, so to speak, which leads to a higher entropy value. So as you go down a group on the periodic table, you're increasing the number of subatomic particles, and therefore you would be increasing the entropy. Okay, let's take a look at, I've deleted quite a few things from your book, but I'm just gonna, are your words overlapping on the top of page 43? Yeah. I know, so are mine. Okay. So I believe this is in your text. Okay, so let's look at some more complicated molecules here. In this table, we have nitrogen and oxygen in different molecules. The simpler the molecule, the lower its entropy. So here we have nitrogen bonded to oxygen. So this would be the simple molecule. It has a standard entropy value of 211. But as you get more complicated from N2O to N2O4 to N2O5, we're adding more and more of each type of atom. This is the most complex molecule. And this one is going to have a lot more bonds, and we can twist around those bonds, and I can do different configurations three-dimensionally in space. Therefore, it would have higher entropy. So this would have the highest entropy because it's the most complex. And then this NO would have the lowest entropy because it's the simplest. Easy enough? Okay. Let's talk about how entropy is dependent on temperature. Okay. So the entropy of a substance is strongly dependent on temperature. This is because as particles gain kinetic energy from the temperature increasing, they're going to be moving more randomly, more chaotically, and in different locations, right? More often. Therefore, you would expect the entropy to increase. So as you go from a solid to a liquid to a gas, the entropy is increasing, okay? The only movement you're going to have for solid particles, as we discussed much earlier in the school year, was that those particles will vibrate and oscillate in place. So if you're looking at iodine here in this table. You've got solid iodine, you've got it dissolved in water, and then you have iodine vapor. So here for the solid versus the gas, you're going to have the lowest entropy because you've got restricted motion for those particles. And over here, you're going to have the highest entropy for those gaseous molecules because they're going to be moving the most random. They're going to have completely unrestricted motion. Okay. So what I want to do is let's take a look at the quick check. We're going to do questions 1 through 4. You tell me, how do chemists define entropy?
State of disorganization.
Okay. What is the third law of thermodynamics?
At 0 Kelvin, it's 0.
Uh-huh. Okay. Which of these two elements has greater entropy? Silver or copper? Explain. Samantha, look at the periodic table where silver and copper are. They're number 29 and 47. You tell me which one.
Copper. I mean, sorry. I thought. I'm not. Silver, because it's.
Tell me why.
Because it has a higher.
Okay, what does it have more of?
Entropy.
But why? It has more of what than copper? Which subatomic particle would it have more of that could occupy more locations outside the nucleus? What subatomic particle is outside the nucleus? Two of them are inside the nucleus, one is outside. Electrons. So silver has more electrons than copper. So that means that there are more positions those electrons could occupy, and that would lead to an increase in entropy. Which of these two compounds has greater entropy? Liquid water or liquid hydrogen peroxide? Explain. Yeah, so hydrogen peroxide. Because it's more complex. It's going to have more possible configurations and can twist around the additional bonds that it has that water doesn't have. And that gives it a higher entropy. Okay, questions on that? Okay, let's go on and let's talk about chemical reactions and entropy changes. Now, generally speaking, a chemical equation alone does not contain enough information for you to reliably determine whether the entropy is increasing or decreasing during the reaction. Okay, so technically you can only determine that by looking at the standard entropy values in the table. Okay, but since we aren't going to be actively using those standard entropy values in a table, what we're gonna do is we're gonna just generally determine whether entropy is increasing or decreasing by using a couple of sort of definitions. So let's take a look at the next page. Okay. Entropy usually decreases when gas particles combine into fewer particles. Okay, that is definitely going to be true here. Okay, so let's take a look at a couple of examples. Right here, I'm going to put a box around this reaction. We're going to count how many gas particles are on the reactant and product side, and we're going to do that using the coefficients. Okay, so here you've got 2 plus 1. So I have 3 gaseous reactants. I've got 2 H2 and 1 O2, and then I've got 2 gaseous products. So since we combined from 3 to 2 gas particles, we went to fewer gas particles, we can say that the entropy is what? Yeah, we can say that the entropy is decreasing here. Okay. Let's go to the second example right down here. How many gaseous particles are on the reactant side? Tatum, how many gaseous particles are here on the reactant side? Look at the states of matter. How many gases are on the reactant side? Okay, what's the state of matter for something that's a gas? Like, what do we have in parentheses? How do you know it's a gas? There's a G. Okay, do I have any little G's in parentheses on the left-hand side of the reactant? No. Okay, so there are 0 gases on the reactant side. How many gases are on the product side? What's the coefficient there? 1. So I have 1 gas on the product side. So the entropy should do what? Increase. Okay, let's take a look at another example. Let's look at this right here. How many gas particles are on the reactant side of this reaction? Yeah, I have 1. How many gas particles are on the product side? 2. Entropy increasing or decreasing here? Increasing. Okay, let's take a look at a different example. Let's look at the iron combining with carbon dioxide. Okay. For this one, I have 3 gas particles on the reactant side. I have 3 gas particles on the product side. Okay. Even though I have the same number of gas particles on each side, what I'm going to do is I'm going to count how many gaseous atoms are on the reactant and the product side. So here I have 3 carbon and 6 oxygen. Would you agree with me? What's 3 plus 6? 9. So I have 9 gaseous atoms on the reactant side. On the product side, I have 3 carbon, 3 oxygen. 3 plus 3 is 6. So I have 6 gaseous atoms on the product side. So would you predict that the entropy is increasing or decreasing? Decreasing. Okay. Okay. Now, let's go ahead and let's talk about, well, let's look at some sample problems. I think we are ready for that, actually. So let's go to this next page here where these practice problems are. It says predict whether entropy increases or decreases in each of the following and provide your reasoning. Why don't you guys do numbers 1, 2, and 3 on your own, and let's see what you come up with. Okay, Annie, why don't you do number 1? Go ahead and walk me through it.
So there's 0 gases on the reactant side, but there's 1 gas on the product side, so that means the entropy is.
Okay, good job. Catherine, you want to do number 2? On the reactant side, how many gases are there? Yeah. There's 8 gases on the reactant side. And then how many gases are on the product side? Yeah, I have 8. So when I have the same number of gases on each side, count how many atoms there are. So how many gaseous atoms are here on the reactant side? Just multiply the 8 and the 2. Yeah, so you have 16 gaseous atoms on the reactant side. And then over here on the product side, you've got 8 sulfur atoms and 16 oxygen. So 8 plus 16 is around 24, I think. 24 gaseous atoms. So would you predict that the entropy is increasing or decreasing? So see how I have more gas atoms on the product side? So that I did to begin with. So gases are more random in terms of their motion. So I would say that the entropy is increasing. Okay. Okay. Let's take a look at number. You could also argue. Do you see how this sulfur was a solid, and now it's in the gas phase? You could also argue that's also why the entropy is increasing. Okay. For number 3, yeah. Yeah, I would definitely say the entropy is increasing because that ice is melting. And the liquid particles definitely get to move more randomly. They can slip over each other than they do in the solid phase. Okay. Okay, what I'd like to do is let's take a look at the 10.4 review questions. Okay. Take a look at question number 1. Answer A, B, and C, and then let's go over that. Okay, what did you put for A?
Which one?
Gas. Right, because gas particles have more random motion than liquids do. How about B? SO3 because it's a more complicated molecule than the SO2 is. It's got another bond that it could twist around. How about C? PB, because PB has more what? Electrons, they can occupy more random spaces. Okay, we're not gonna do number 2 at all. So you have the rest of today and you're gonna have Monday to work on PB pivot CT lab number 15. Okay, so I'm gonna let you work on that now.
Is there any homework on?
There is no homework on campus.